So we're with 3.5, even though this is the fifth topic of the Year 10 physics, we're doing it as in the third topic. We're going to start up at the top here, explaining the differences between longitudinal and transverse. So there's two types of wave. Obviously the longitudinal, it says there, and transverse, and we're going to give examples. So a transverse wave is where the energy, and this is a definition you're just going to have to remember, the energy moves at right angles, so 90 degrees is the same as a right angle, to the direction of the wave. Any EM wave, electromagnetic wave, such as light, radio waves, and gamma, is going to be an example of a transverse wave. Now, it's hard without showing you actually what I mean by that. You're probably not going to know this yet because this is an introduction to the topic. But a transverse wave, if I can kind of show you if this works by it, and then the energy. So even though the energy is going this way, the direction, the energy is going, I might as well start that again. So we are here with features of waves. It's the fifth topic in the Year 10 core, but we're doing it as the third topic. I'm going to start on the top. It's going to be hard to visualize these waves without some sort of diagram, but the first one explains the difference between longitudinal and transverse. So if this is just an introduction, you've got two types of wave, longitudinal and transverse. Like I said, without showing you, it's going to be hard to visualize these, but here's the definitions, and you do need to know these. A transverse wave is where the energy moves at right angles, or 90 degrees, to the direction of the wave. So if the wave is going this way, okay, the energy is going up and down. And you'll often see it, I don't know if this will come out, but you'll often see a transverse wave like that. And then longitudinal, on the other hand, is where the energy of the wave moves in the same direction as the wave. So I'm not going to draw that diagram, but if the direction of the wave is this way, then the energy of the wave is going to follow, and there are diagrams we can use to show that. Some examples of transverse waves, things like light, radio waves, gamma waves, and when we get into the electromagnetic spectrum, or the EM spectrum, you'll see that it's any EM wave. We can also say that they're water waves as well, but let's keep away from that. So any EM wave for transverse, and then longitudinal, sound, ultrasound. Sound is your main top answer there, because sound actually needs particles to move through. So longitudinal needs a medium to move through. You know, they need to push particles against each other, whereas a transverse wave can just go through a vacuum. That's how we get energy from the sun. Space is a vacuum, yet these waves can still travel through space. So light, radio waves, gamma waves, things like that, they can travel through a vacuum. Don't need any particles, whereas longitudinal, they need something to move through. We're going to go straight down then to reflection and refraction. So reflection is basically when light bounces. It's the bouncing of light. And I've got a little diagram here. So you can see that this arrow coming in is called the incident ray. And we label that with a little I for incident ray. And I've got a little arrow showing the direction. And that's all these things are, these little green ones here. They're wave fronts. They are the distance between waves. Okay? You know, there's a question on one of the early papers, and they left these wave fronts off. And it was up to you to know that the wave fronts are going to be exactly the same once they're reflected. So you would have to draw these in then. You'll probably come across that question. But this is your reflected ray. Okay, so it goes in, bounces off the mirror, and comes back at exactly the same angle. These angles here, this angle theta and this angle here, I equals R. So it's going to come back at exactly the same angle. If you change this angle, if you go in a little more shallow, you're going to come back out a little more shallow. So I've said the rule is the angle of incidence, incident ray, equals the angle of reflection. Bang, out it comes. Okay, and that's pretty much it for reflection. Okay, you don't need to know more than that. This line here is the normal. We always measure the angle off the normal. just in case this mirror is at a different angle. So you'll always measure it from this dotted line. So never use, you'll never see the angle measured from there to the mirror. You'll always see it measured from the ray of light to the normal, this dotted line, which is 90 degrees to the mirror. And then this one is refraction. So refraction is the bending of light. Now, if you put a pencil in a glass of water, you will see that it'll slightly bend. The pencil won't actually bend, but the light off the pencil reflected to your eyes will bend. So what happens is it comes in, and again, I've got my green wave fronts. Now notice as it goes through this, so this is in air, this is your glass block. So think of this thing as a glass block. As it comes through now, these wave fronts become less, so they're shorter. Okay, R is your refracted ray, and it actually bends towards the normal. Can you see how the angle of incidence there comes in? This is your angle coming in between your normal, and then it actually bends towards the normal. Okay, in a more dense. If it's less dense, it will bend away from the normal. You'll see this line then sort of come over here slightly. But because it's more dense, it will bend towards the normal, and the wave fronts become less. Okay? The wave fronts will change. And then it'll come back out at exactly the same angle as it went in. Okay, that ray of light. And we can do experiments for this in classrooms with a laser and some glass blocks. I said the angle of refraction there, R, bends towards the normal, and the wave fronts change. It decreases in shallow water, so you need to know, this spec has got a big thing with deeper water and shallow water. If it's coming from deep water to shallow water, they will decrease. Okay, these wave fronts. I'm going to keep going down. What does the term radiation mean? Well, radiation is just energy given out by an electromagnetic spectrum. So when you get X-rays and gamma rays, okay, they're very... we say that they radiate. I mean, all waves radiate anyway. But the higher the energy there is, the more dangerous it is. So down on the bottom page, there's an EM spectrum. I'll talk a bit more about radiation there. But basically, high energy particles emitted from radioactive materials causing ionization. Ionization. I don't know if you've done this in chemistry yet, but to make an ion is just a charged particle. Basically, they either lose an electron or gain an electron. They become a positive or a negative. We call them cations or anions. And the way I always remember that is anions. It sounds like onions, which is like a negative. So, yeah. So these high energy particles, they emitted from radioactive materials. We'll do a lot of this in year 11. Causing ionization. And then what is ionization of cells? Well, they cause damage to the cells. Basically, they're stripping electrons and protons from your cells, causing mutations. Okay. Let's go down here. So we've got a little bit of maths now to do. We've got red light travels at 3 times 10 to the power 8 meters per second. So that is just 3 with 8 zeros after it. If the wavelength of the red light is 450 nanometers, how long does it take to travel 10 kilometers? Now, I haven't got to really do any conversions here because we're going to give the answer. So let's have a look here. So we've got speed, 3 times 10 to the power 8 meters per second. I'm going to do anything with that. I've got my wavelength is 450. My distance, so how long does it take, is 10 kilometers. Now, if the wavelength is that, what it's trying to do is to trick you. It's giving you 1, 2, 3 things, but it's asking how long it takes. And the only thing you've got with time, really, is distance, speed, time. So this 450 nanometers is trying to confuse you a little here, as it just did with me then. Because I was wondering where that was coming from. I was thinking I got to convert 450 now nanometers to meters. I was thinking about going to show you the prefix page and how we do that. So nano is just 1,000th of a millimeter again. So if we're coming from meters, we've got to, if we're going from small to big, remember small to big is divided. So we'd have to get that into meters, we'd have to divide that by 1,000 to get it into millimeters first, and then we'd have to divide it by another 1,000 to get into meters. As it stands, I'd probably just confuse you here. We don't need this one anyway. So I've just gone off on a bit of a rant there. The main things I'm interested in is speed. And there's my speed, meters per second. It's already in meters per second, so I don't have to convert anything. And I've also got my distance to be 10 kilometers. I do have to convert that now back down to meters. So I'm going from big to small now. Big to small, you multiply. And we're going to times that by 1,000. So I've got 10,000 over 3 times 10 to the power 8. And that comes out to be 0.0003 seconds. Or we can say 0.3 microseconds. Or milliseconds, sorry, not microseconds. Write down the wave equation. Well, that's what I thought we were going to use because I saw nanometers there. But basically, this is the wave equation where you got speed, meters per second. You got frequency, hertz, okay, and you've got this lambda here, which is wavelength, and that's in meters. Here's the electromagnetic spectrum I was on about just a couple of minutes ago. Probably going to start a new video on this one. So if I write